me. Hello, everyone. Yeah, welcome to our next session. Why we hate database programming. And yes, it's a very offense title. But at the end of this session, we all should love database programming, right? This is my intention with this talk. Let's have a look on the agenda. First of all, I want to talk a little bit about the challenges of database programming in Java and why so many Java developers told me in the last 20 years or so that they really hate database programming, and why they hate database programming. Then let's talk about a complete different approach. It's a Java native approach of database programming and data processing with pure Java. And of course, I have prepared a small live demo, and I'd like to introduce you to the working principle, and then we will have some time for Q&A. My name is Markus Kett. I'm CEO and co-founder of MicroStream. It's a small company. The software we build is open source, and it's now part of Project Helidon. It comes with a next official Helidon release 2.4. MicroStream will be part of Project Helidon, and the last 20 years or almost 15 years, I've been working on Java development IDEs. So with my team, I have built 2 complete Java development environments. The first was based on Swing. Then the second, we have migrated everything to Eclipse, and it's still available as a free software. The entire framework is open source. Also, it's called it's called Rapid Clips. And our goal with Rapid Clips was always to build a low-code Java development environment that works similar to Visual Basic or Oracle Forms or something like that. Where you can build graphic user interfaces very easily and fast, and build data-driven applications very easily, but with Java and with a really professional programming language where we can do really almost everything. This was our goal, our dream, and everything worked really fine with the GUI builder. So we were able to build beautiful GUI builders, were really easy to use with, to work with. But as soon as we wanted to store data, or our users wanted to store data, then the horror began, because database programming in Java has always been very complicated, effortful, and not as easy as it should be. So this was the reason why we tried to improve the existing database tooling. We worked on the Eclipse JBoss Hibernate tools. We tried to improve the tools. We tried to improve the framework behind that. We worked on improving object relational mapping frameworks, especially on Hibernate, for many years. And this is my basic background. Yeah, why do we talk about that? It's because data, yeah, we call it the oil of the new century, and it becomes more and more important. So more and more applications must process more and more data. They produce more and more data. And yeah, everything is based on data today. All these modern applications, AI, machine learning, virtual reality. So it's all about data. And the big question is Java still fast enough? So are we able to build such powerful applications with Java actually. And many Java development conferences, the participants and the speakers talk about and discuss, are the databases of today still fast enough? That's really a big question, and there are more and more different approaches coming up, serverless functions and or Python. So is Java perhaps a dinosaur? Big question. Let's have a look on that. What's important in Java, and why we love Java actually? So I have learned when I came to Java, then of course I asked the big question, hey, why is Java so successful, and what's actually different to JavaScript? And wow, this was one of the biggest question, because the Java developers told me, you cannot compare Java with JavaScript. It's fundamentally different, because in Java everything is object oriented, and this is the reason why we love Java. It's fully object oriented, and of course it's type safe, and this is super important for us, type safety. And we love, of course, we love abstraction. We love standards, so super important for us. Standards are important, and that we are able with Java to build almost everything and in an elegant way. So we can build elegant object models. We can design almost everything, and clean code is for us very important. So clean code. And of course, good testable code. All these aspects are very, very important for us. And this is the reason, or these are the reasons why we love Java. Okay, fantastic. And I think, I believe, and I'm convinced with Java, we are definitely able to build such applications, such modern applications, AI, machine learning, all the beautiful pictures I showed here already. But the big question is, what's about database systems? Are database systems of today powerful enough? Or should we wait for quantum computers? When we have a look on our database systems, then of course they are really powerful. But actually, the technology based on a 1960s technology. Why? Let's have a look on traditional Java persistence. How does it work? In Java, everything is an object. So we deal with objects all the time. Everything is an object. But as soon as we want to store data, then we leave that object-oriented way. Then we use external database systems, and they were totally different from Java. The relational databases, for instance, they store data in tables. And now we have a problem. Storing objects or complex object graphs in flat tables is actually not possible from a technical perspective, because we have an impedance mismatch here. So we have several impedance mismatches. And this is my personal opinion, this is the core problem why we have all these problems in database programming with Java, because of this impedance mismatch and these fundamental differences between both technologies. How to solve this problem? To solve this problem, we use an object relational mapping framework. And Hibernate here is the de facto standard. What happens behind the scenes? With Hibernate, we are able to write our queries in Java, and then Hibernate generates the SQL code. and sends the SQL to the database. And vice versa, the database never returns objects. So we get a result set from the database, and now the objects have to be generated. And this job is done by Hibernate. And actually, this is a kind of like data conversion behind the scenes. And we do this through every single read and write. However, data conversion, so imagine you want to watch a video, and whenever you want to watch the video, you have to convert the video first. This would be really a problem, because converting takes lots of computing time, and it's always a latency. So you need more computing time, and on our server, we have the same problem with this data conversion when we access the database. And there also we need more computing power, but this increases the cost of infrastructure. And it leads to latencies and makes our systems inefficient. And I would say this is the performance killer number one. What's about NoSQL databases? So we know the NoSQL databases, they do it fundamentally different, because most of them do not use tables anymore. Now, the NoSQL databases, they use different data structure. Key value, document model, for instance, JSON or XML, or we have the column stores databases. We have the object-oriented databases. So with object-oriented databases, we are able now to store objects. Or we have the graph databases. But all these data structure are specific database data structure, and they are also incompatible with Java object graphs. So we have actually the same problem here as well. So here we need an object, we need a mapping as well. Then there are further challenges, because now with NoSQL databases, we have no standards, we have no framework like Hibernate that does the job for us. So here we need a custom mapping, or any other data conversion, for instance, when we use a document database. So same problem here as well. And for developers, we have the challenge that we now have to implement or we have to build two different data models. So one data model on the database side, and we need our Java classes. And now we have to adapt our Java classes to the database model. So the Java developers mostly say now we have to build our database application around the database. And this is what we actually hate, because actually we only want to store some objects, and this is what we actually want to do, only storing our objects, nothing else, and not to deal with database specific functionality and data structure. So are you using stored procedures? Are you using stored functions? Do you love that kind of programming? And if not, why not? Because the database vendors, they tell us to use these database specific functions because they were built to be used in a database application, and we should use these functions. But the Java programmers, they ignore these functions mostly because these functions are ignored by the Java standard. So it's ignored by Hibernate, and so we ignore it in Java programming. Of course, there are always Java programmers, they use stored procedures and stored functions, but most Java developers do not use it. What's about in-memory databases? In-memory databases, this sounds really incredible because it sounds fast. It sounds everything is executed in memory, right? So, but when we have a look on the architecture, then the in-memory database runs here indeed in memory. The entire database system runs now in memory, and the entire database, so all data are also in memory, are kept in memory. So I would expect now everything should be super fast because everything is in memory. But the database itself is runs on a completely different machine. So it runs on a remote server or on a remote cluster. So the database itself runs in memory, but it runs not in the same memory as your JVM and as your application. So we have network traffic between the application and the memory database. And so the query time depends not on your memory, it depends on your network performance. And your in-memory database will not deliver objects to your application. So you need this object relational mapping here as well on top of that. So it depends, the performance always depends on how fast is your object relational mapping. So here we have the same problem even when we use an in-memory database. And the architecture gets more and more complex when we have distributed applications. So then it becomes even more complex. And what we have in addition to our in-memory database is we need a conventional database as well to persist our data. So this means we have a traditional database, and on top of that we have an in-memory database, and then we have our cluster, our application cluster. Then we have to replicate our nodes, or we have to deal with local caches. Perhaps we need a distributed cache on top of that architecture, and then everything gets even more and more complex. Instead of an in-memory database, we could use also an in-memory data grid to store our data in memory and keep our data in memory to accelerate our systems. What is actually an in-memory data grid? With an in-memory data grid, we have no database running in memory. We only store the data in memory. And the data are kept in memory mostly as a key value data structure. Then the in-memory data grid is able to replicate the data in memory between the nodes. And so you're able to scale your memory through hundreds or thousands of nodes in your in-memory data grid, and keep your tons of data in memory. And this is very powerful, of course. And to persist your data, mostly you can use snapshots, or you can use additionally your conventional database. You keep your conventional database, and on top of that runs your in-memory data grid. And then you have a similar architecture to you in comparison to an in-memory database. And if you have a distributed application, then we have this architecture here. So it gets even more complex. Very similar to the in-memory database architecture. The problem here is when we read the data from the memory, we are not access directly to a memory. So we have to go through network. And here we have the same problem. So it does not depend on your memory speed. It depends on your network performance, how fast data access will be. And we need this mapping. So here the same problem as well. We always need a mapping. And then let's have a look on a local cache. Oh, this should be really fast, because local cache means we access directly to memory, and this should be incredibly fast, right? Access to memory should be, let's say, sometimes microseconds or nanoseconds. But have you ever measured the query or the access time of your local cache? We have measured that, and then we saw it is much slower than it should be. Mostly when we read the data directly from our local cache, we get a millisecond response time. And so when I measured that for a very first time, then I was shocked, because it actually should be microseconds or nanoseconds, but not milliseconds. What's the problem here? The problem is that even when we have access directly to a cache, then we need this object relational mapping. So conclusion, whatever you use, so you can use whatever it is on a market. So in-memory databases, relational databases, you can use NoSQL databases, graph databases, even when you use object-oriented databases. No database will store your Java objects as they are in the memory. So in all cases, we need a mapping or a data conversion. And as soon or as long as these systems are different, or the technologies you use are different, then sooner or later you will have performance issues, or your system will be getting more and more complex. You cannot avoid this. And this is because of the core problem that the systems are different, the data structure are incompatible. And for us as developers, we have to deal with completely different data structure. So we have to build our entity classes. We write our entity classes in Java, and we have to build our object model and implement our data model in the database. So double effort. Then we have to deal with a database-specific query language. And actually, we love type safety and object-oriented programming. But when we have a look on our query code, then sometimes we see there are SQL strings. SQL strings included in our Java code. And this is not really type safe and is not good testable. So we leave this object-oriented way as soon as we want to store data. And this is what I meant with, this is why we hate database programming, because we leave this object-oriented way, we leave this Java native way, and we have to deal with complex external systems that work different. We have to deal with complex frameworks. And then when we use Hibernate, often the performance goes down. So we have to implement additional caching layers, and then we have to configure our caches, and it gets more and more complex. And so this is why we hate database programming. So how can we solve this? Let's have a look on a completely different approach. We call it ultra-fast in-memory data processing. Why? Because I am convinced that Java as a programming language provides almost everything we need to build super fast Java in-memory database applications. The function principle here is called system prevalence. What's system prevalence actually? Java already provides the perfect data structure. We have objects, we have object graphs. And with object graphs, we are able to build individual data model. So we can design our data model completely freely. So we don't have to adapt our database model to our database specific data structure. And this data structure is already a multi-model data structure. Why? Yeah, it's because you can use everything. So you can build up a very complex graph structure with circle references, but you also can use and you can use a simple list. So you can store only one object. You can store a list in memory. You can build up complex data structure, complex graph. So it's and you can use all Java types. And this is why I call it the perfect multi-model data structure. We can use collections. We can use objects from third parties, and we only need to write Java classes, right? That's all. No mapping at all. System prevalence is the simplest way to provide persistence for your POJOs, for your Java classes. And it's an architectural pattern that combines your system images with transaction safety by using snapshots. That's the function principle. So it's really a very simple functional principle. In prevalence system, the state is kept in memory in a native format. So it's provided by the JVM, and all transactions are shown, and system images are regularly saved to disk. And Martin Fowler has already described such a system in 2011 already, where he was very excited about the performance of such an application. And yeah, this was 2011. But of course, when you think about snapshots, then we will see some challenges from the scratch. So system prevalence is linked to various challenges, and yeah, perhaps this is the reason why it's not so popular in practice, right? So what's the problem here? The snapshot size is very huge, or can be very huge, and if you have to snapshot huge amount of data in memory, then the snapshot time will be too long, and between the snapshots you can lose data. So this is not really cool. And if you build a microservice, for instance, then it's important that you have a very fast startup time. But if you have to restore your entire in-memory database, then it takes too much time. So it's not, this functional principle is not suited for microservices. And with this approach, you are limited to the RAM size. So the database size can't be bigger than your memory size. This is also not really cool. And when we think about huge memory sizes, then yeah, we will instantly think about garbage collector issues and latency because of garbage collector pauses. Then to get these snapshots, Java serialization has to be used, and Java serialization is linked to security issues as well. Then there are lots of further questions. For instance, what's about if my classes change? How can I migrate my data? How can external systems get access to my in-memory data kept by object graph in memory? So here we have so many problems and challenges, and this is the reason why this, I would say, dreamland solution has never worked in practice, or has never become that popular in practice. But now I like to introduce you to a new framework, a new persistence library that bases on this system prevalence approach. And with this Java library, we have eliminated all of these challenges, and we have eliminated all of these problems. This persistence library is called MicroStream. It's open source, and it's also now part of Project Helidon. And we are very proud to be contributors to Project Helidon. How does MicroStream work? MicroStream in core is a fundamentally new written serialization. So we have written it from scratch. So very important, it does not base on the traditional Java serialization. On top of the serialization, we have built a persistence layer for the JVM. Additionally, we have built the same or a similar persistence layer for Android. On top of that, we provide so-called legacy type mapping and additional tooling that care for things like what happens when my classes change. So we have the legacy type mapping. Then we have a kind of like garbage collector for the file storage, where the garbage collector operates on file base and removes legacy objects from the storage, similar to the garbage collector of the JVM. Then we have a file system abstraction. We have database connectors. We have a REST interface, and on top of the REST interface, we have a storage browser where you can browse through your storage data. And we have some native backup functions. So let's have a look on the architecture now. Here we have our Java application, or our microservice written in Java. We have our object graph in memory, and now our object graph becomes an in-memory database. And we have MicroStream as a storage layer, as a Java library that is that stores the object graph completely or only single subgraphs. And this is brand new. So with MicroStream, you're now able to store also single subgraphs and restore single subgraphs in the memory when it's needed again. The data are stored in a binary format. And so this is the reason why we're able to store the binary data by using the database connectors in any kind of database system. So you can store the data your binary data in a relational database as well as in NoSQL databases. And you can even store and persist your binary data into distributed systems like in-memory databases, in-memory data caches like Redis or Coherence. You also can store data in Kafka. And again, it's very important to mention again that we do not use snapshots to store and snapshot the entire object graph. You can do that, but mostly with MicroStream, you will only store and snapshot single object references. So you can store single subgraphs, and you can load, reload, and single subgraphs by using lazy loading. And with this approach, all conversion are eliminated. There is no more object relational mapping or any data conversion, any conversion of your objects into any database specific data structure. That's completely eliminated. Simple architecture, it saves lots of CPU power. It minimizes your latencies, and it enables you now to query your data in memory. So you now can query your object graph in memory and use your object graph in memory as an in-memory database. And this is super fast because now you can use Streams API, Java Streams for searching your object graph. And this is super fast because searching even huge object graphs in memory takes only microseconds, up to 1,000 times faster than a traditional SQL query with additional object relational mapping. Cannot believe that I have prepared a brief demo. Here we can see two applications running in parallel. One application, or first of all, it's a bookstore demo. So it's an online shop demo with some demo data, about 250 gigabyte of data in memory. And here we use one application that uses Hibernate and EH cache. Here we have a hot EH cache. So here most queries hit the local cache. You can see the query code. And under the hood, we use an Oracle database. The second application uses MicroStream to persist the object graph or the subgraphs. And here we query the object graph in memory with Streams API. You can see the query code. And now you can see each query is executed sometimes 10 times faster, sometimes 100 times faster, and sometimes 1,000 times faster in comparison to the JPA query. You can download this from GitHub, play around, try it out. It's incredible. It's pure Java. And yeah, you can use it for your own incredible fast in-memory database applications. You can see the supported database systems and further database systems will follow. MicroStream is a tiny Java library. You can download via Maven, included in your own Java code. The only requirement here is Java version 8. It also runs, and this is very interesting, with all JVM languages. It runs on Android and it runs on GraalVM native images as well. What are your benefits of that performance? What can we do with performance? Okay, you can do things that were not possible before. Now you can build incredible fast AI apps, machine learning apps with pure Java, and build everything that was impossible before with traditional data storage approaches. It saves lots of computing time. Yeah, because if your queries are executed up to 1,000 times faster, then you will save lots of computing power, because you do not have these object relational mapping again anymore. So you save lots of computing power. And one of our clients, it's an well-known insurance company. They run an application in 22 countries. And normally you would have to build a huge cluster for that and run a huge cluster. But this application runs on only one single machine, or in other words, actually only one single machine is sufficient, or the power of only one single machine is sufficient to run this application. Honestly, we have 2 applications running because it's high available, but we save up to 90% CPU costs and this cost of infrastructure in the cloud. And this is really incredible. And it's because of the power of the JVM. And for developers, this is super convenient, because now you only have to deal with only one data structure. It's your Java classes. So no more second database specific data structure, no more mapping. Okay, let's have a look on the code. How does this actually work? Here we can see one simple Java class. It's a customer class. So what we see is nothing specific. So there are no annotations. You don't have to implement specific interfaces. There are no specific superclasses, just POJOs. You can use all Java types that are supported by MicroStream. So it are the almost all Java types are supported, and we support all useful types. So for instance, it's not useful to persist a thread or so. You can use all objects from third-party libraries, so this is also possible. Yeah, and easy to implement. You can build up your own object models. You can build your object model completely freely. So there are no specific rules or so. You can really use any object graph of any complexity. Yeah, use only one object, use only one list or so, but you also can use a complex object graph with circular references. How to persist objects? It's only one store method. You only have to call one store method to store your object references, and only the changed objects are stored. So if you have a huge collection and you change only one object, then really only one changed object will be stored persistently on disk. And so it's the delta is stored only. And each store method is an atomic operation that is transaction safe. The performance is really incredible because there are no data conversion, no mapping behind the scenes. So it's almost the performance that your hardware provides. So if you use a ultra fast SSD disk, then your performance will be almost that fast than your hardware is. You can use also channels, which means it's multi-threaded. The more cores your hardware provides, the faster will your I/O operations be. The data are stored persistently on disk by using appended log strategy. So each store method will store your object appended to your storage. So if you call a store method 100 times, your object reference will be stored 100 times appended to your storage. So your storage will grow more and more. But this is not a problem because we have this kind of like garbage collector that operates on a file storage and removes your legacy object from your storage automatically behind the scenes. You can use, I've mentioned it already, you can use channels and to parallel your input-output operations. How can we load data into the memory again? Initially, when you start the application initially, then MicroStream loads the entire object graph into the memory. But now be careful, it's not all data are loaded. Only the object IDs will be loaded into the memory. The object IDs only. And then you will decide which object references will be loaded initially by using eager loading, or which objects you want to load on demand by using lazy loading. And it depends on your use case. So you can do really both. So if you have a small database and you have lots of memory, then of course, and you build let's say a monolithic application, then you can load the entire database in your memory. Then you have a fully in-memory database. Then all queries are super fast, and you have a no latency system. And yeah, everything, it will be the maximum of speed. But the advantages are you have a low startup time, or you might have a low startup time. So it will not be suited for microservices. If you have a really huge database, but you only have some gigabyte, let's say only 4 GB memory, then it's not possible to load the entire database in the memory. Then you only load the most important data initially, or you load no data. So then only the object IDs of the object graph are loaded initially. Then this will be super fast. And then this approach is also suited for microservices, yeah, because with microservice, you need the maximum of fast startup time. And then you load data on demand only by using lazy loading. And lazy loading is really, it's really super convenient because you don't have to deal with traditional database SQL queries or submitting any SQL code or something like that. You only have to call get methods. So you only have to call a get method, and then you get the object by the engine. If the object is already in memory, then you will get it from the JVM directly. If not, then MicroStream loads the object from the storage and returns the object in a way you used to use with object-oriented programming. So this is a very convenient programming model. And one of the most asked questions is, do I have to deal with the memory? Do I have to care for memory management? The answer is no. Everything is provided by the JVM. So the JVM cares for the memory management. You can influence your lazy references, of course. So you can decide at any time if you want to clear lazy references, to remove objects from the memory, to save memory, but it depends on you. And if you have concerns of in terms of garbage collector pauses, then you should try different JVMs We have tried, for instance, Azul JVM, and with Azul you can work with even 10 terabyte of data in memory without garbage collector pauses. So very interesting. So everything is possible in Java. So you can build the fastest systems with pure Java now, and everything is core Java. And yeah, here we can see how the queries work. You simple use Streams API. You can also use GraphQL for querying your object graph. And with GraphQL, you can provide third-party applications access to your object graph, to your in-memory database. And via REST, you can provide access to your storage data. So MicroStream, of course, leads to a paradigm shift in database programming, because the traditional way is we have our Java application, and we have our database server that runs on a remote machine. The database runs on a remote machine, runs on a database server, and we query and we execute all queries on the database server, and the database server returns the data to our Java application. With MicroStream, this is a different approach. Here we load the data from our storage into the memory, and then we query the object graph in memory. So our database is located in memory and runs within your application JVM process. If you miss anything in MicroStream, you should have a look on the fantastic Java ecosystem. Here we can find almost everything we combine with this approach. For instance, Lucene for full text search, powerful full text search, GraphQL mentioned already to provide third-party applications or BI tools, providing them access to your in-memory database, to your object graph in memory. You can choose between several JVMs that are fully optimized for huge memory sizes. So everything is already existing in the powerful Java ecosystem. Yeah, MicroStream is only a plain Java library. So every 6 months a new release comes out. So this week or next week we launch MicroStream version 6. It's available as open source, and there are, of course, some requirements. And with MicroStream, there are also challenges I like to talk about. For instance, it's really not built for DBAs. So if you a DBA, then you will hate MicroStream, because it's built for Java developers. It's mostly Java developers love it because it's fully object oriented, and it's a Java native approach built for Java developers only. Currently, it's a single node. It's built for single node applications, so which means you have only one JVM and only one data source. But we are already working on a distributed system. The prototype is already running. So hopefully in some months we can provide MicroStream cluster where you can build up distributed systems by using MicroStream. You have to care for concurrency by using a traditional database system. The database system cares for concurrency, but what we have learned in the last 15 years or so in application programming, that Java developers have to care for concurrency anyway. So, but you have to know that you have to care for concurrency. Sometimes it might be challenging to allow external systems access to your data. So, but this can be used with REST or can be solved with REST or GraphQL. Yeah, and I mentioned it already. The only requirement from a technical perspective is Java version 8. With MicroStream, you not only get a persistence library, beyond persistence, it's might be interesting to know that MicroStream is in core a serialization, and it works fundamentally different to Java serialization. What's the benefit for you guys? It's with the Java serialization, we have security issues. Java serialization enables you to inject malicious code through and execute malicious code through deserialization automatically. So, and you cannot do really things against it. So it's very hard to do anything against this. With MicroStream, it works fundamentally different because we do not use reflection, and it's not possible to inject and execute malicious code through deserialization. So if you are interested or looking for a high secure serialization, then you should have a look on MicroStream. Yeah, you can start with MicroStream via downloading from GitHub or MicroStream.1. We have many videos on YouTube, and with the next Helidon version, MicroStream will be part of Helidon. All right, that was MicroStream in a nutshell. Any questions?
Thank you for the nutshell. No, I see no question in Q&A.
Okay, yeah, this was the reason why I hope I could explain this a little bit better, why many Java developers hate database programming, and why database programming with pure Java and MicroStream is only a small and a piece of puzzle, and only the missing piece of puzzle, and why database programming with pure Java is that elegant and is that really a lot of fun and is that fast and incredible fast in comparison to traditional storage approaches. So check it out. It's free. You can also combine it with JPA, because in a microservice infrastructure, you don't have to decide between a relational database or MicroStream. So you can make this decision for every single microservice. And often you have hundreds or thousands of them.